Welcome everybody. My name is Ramchandra. I am an IIT alumni. I have started the channel CIVIL-MECH-MATHS Concepts with a view to impart sufficient knowledge in concepts of civil and mechanical engineering along with engineering mathematics, so that the aspirants writing engineering services examination of UPSC and civil services examination of UPSC, staff selection commission examination for junior engineers, and various public sector companies examinations, PSC examination, and then GATE examination and CSR examination, where the topics of civil and mechanical engineering will be helpful. And I have taken the first topic in my whole course. It will be a series of lectures on civil and mechanical engineering subjects, and the first subject I have taken is fluid mechanics. The reason behind it is that it is a common subject for both civil and mechanical engineering aspirants for all the examinations which I have quoted above. And also the fluid mechanics carries a weightage ranging from 10% to 35% in various examinations. I have taken the toughest topic in fluid mechanics, which is turbulent flow, as the first topic, so that you can appreciate the way I teach the toughest topics also in a very simple manner, so that you can very well easily understand the concepts and do the questions given in the examination. It's not only for questions in the examination, it is for developing the concepts and also applying for your day-to-day life. And the first question which is appearing on your screen, which you will be able to answer when you complete this lecture. And I request everybody to go through all my lectures. Even in engineering mathematics, I published 7 lectures in YouTube on the same channel name, and you can view them. This is the first of its kind for civil and mechanical engineering candidates. And in this, if you see, I have taken a rough turbulent flow in a pipeline with a particular diameter, and it has a velocity gradient, and also at the wall, 30 mm from wall, we have to find out the wall shear stress, which is a very conceptual question and it requires a lot of thinking. Kindly view my video till the end, review and subscribe to my channel. Today we will be talking about fluid mechanics, lecture 1, that is on turbulent flow. People may ask me why I have gone to turbulent flow directly instead of going from the basics. A person preparing for the competitive examinations has already might have completed his 4 years engineering graduation or 3 years diploma in engineering, and already had some experience and some understanding of the basics of the engineering subjects he has done, and he definitely might have practically completed certain experiments in the laboratory which might have also given some imprint in his mind about the type of the subject he has studied and the basics of the subject. Now, if I take a typical topic like turbulent flow in pipelines, then that will be more useful to the person whom I am addressing to understand the advanced studies in that particular topic, or to clear the backlog of concepts in that subject, rather than I start defining what is pressure. Pressure is nothing but force by area. Area is perpendicular to the surface. All these things we had done in our 12th class and our basic engineering course while studying in our diploma or in our degree courses. Now, I started this turbulent flow because I want the persons who are, after listening to my lecture, the persons who are appearing in the examination, they have to be clear of their concepts and score high. For scoring high, repetition of the definitions repetition of the force, area, pressure, then area of the triangle, area of the rectangle. These are all things we had done already. Now I want to go little bit ahead of what is being taught from the introductions of the subject to the little bit advanced topics and little bit confusing topics. Maybe regularly I will be taking the topics like this, like now I have started with turbulent flow in pipelines. Like this, I go for laminar flow in pipelines, then drag and lift, then turbines and pumps, so that the advanced topics will get sufficient amount of interaction with me, with the aspirants, and sufficient amount of attention by the aspirants. And let me, from whatever notes I had prepared, I will just make a note of it today. We'll discuss about only the nomenclature and little bit of definitions with a little small figure. Let us draw a two-dimensional XY plane. This is X, this is Y. Now, let's have one curve like this. I'll explain about this graph, definitely. Just concentrate, a curve like this. du by dy, this is linear. What is du by dy? U is the velocity, y is the distance from the wall of the pipeline. Then du by dy, it has the dimensions. You see, just see, du by dy has the dimensions. Velocity is L by t and it is L. The dimensions of du by dy are t to the power of minus 1, which is nothing but per second. Whenever you find out the variation of some quantity with respect to time, ds by dt, we will call it as rate. This is L by t, L into t to the power of minus 1. Then, whenever we call like dy by dx, y is also, we call it as a length, let us say, and x is also length, then it will be L to the power of 0 dimensionless. For example, if I say velocity du by dt, then it is called as acceleration, that is equal to rate. Then if it is du by dy, then this is L into t to the power of minus 1 by L. This is called as gradient. Whenever any quantity divided by some other quantity of distance with respect to distance, if you measure the variation in a particular quantity due to the variation in the distance, then it is called as a gradient. When variation in velocity with respect to time when we calculate, it is called as a rate. Now you tell me, du by dy, can we define it as a velocity gradient? Because usually, without understanding the meaning, people start writing. And afterwards, they get confused between du by dt and du by dy and du by dx and dy by dx. When we do the dimensions, when we find out, then we can easily find out that this is velocity gradient. Now this is the velocity gradient. In examinations, what they do, velocity gradient per second they will give. Then people start checking about what is the dimension, why it is per second, why it is so, why it is. It's nothing but change in velocity per change in height from the change in distance from the wall. Let us say this is the wall. This distance from the wall, this is the wall. Wall means don't think that it is a wall. It is a pipeline surface. Pipeline is there. This is the pipeline or some conduit flow. Flow is like this. And this is the distance. And let us say this is the radius. This is the distance. This is the radius. This is the distance. And at the distance, at the particular wall, what will be the velocity of the flow? Here mean velocity, let me say capital V. And I told you du by dy, that is a linear velocity gradient. That velocity gradient, this from this you might have understood, velocity may be like this. And this is the gradient. At this point y, du by dy is the velocity gradient. V is the mean velocity, centerline velocity. And u is the velocity at the point y. Now, with this little concept, I spent about some 5 minutes on this because you people have to understand this difference. Until and unless you understand this difference, you will not be understanding the turbulent flow fully. Now, velocity of flow from here to here, just see what I am drawing. I will explain everything. This is turbulent. Laminar sublayer. Whenever product flows in a pipeline, what happens? The centerline velocity will be the maximum velocity and the velocity at the wall will be the minimum, and the V, capital V is the mean velocity of the total flow, and U max is the maximum velocity. This is the centerline velocity. U is the velocity at any point. U is the velocity at any point y. And in between this velocity U, this is the velocity U, let us say. This is a velocity profile I am drawing in a pipeline for a flow, fluid flow. This velocity U at y, and at that particular point y, where velocity is U, there the velocity gradient is du by dy. And the centerline velocity is the maximum velocity U max. And capital V is the mean velocity. We can even say capital V mean. Mean velocity, because velocities are changing from wall velocity to centerline velocity. A profile is made. That profile, if we say this is a parabolic profile, parabolic, let us assume it's a parabolic profile. The upper, there will be a laminar flow. Here, wherever velocities are less, what is that? It's called as, what is Reynolds number? Reynolds number is rho V d by mu. This is the Reynolds number. Here V is equal to velocity. If V increases, Reynolds number increases. For the same product fluid, it is a fluid property. It can be constant. It is a physical diameter of the pipe. It can be constant. And this is density, fluid property. It can be a constant. Then Reynolds number is directly proportional to velocity. If velocity is very high, Reynolds number will be very high. When Reynolds number is very high, the flow changes from Reynolds number is very high, means turbulence is very high. Up to this much, once you people have understood, then I will proceed further with my nomenclature. Let us say, I told you wall. Wall is nothing but the pipeline edge. We can even rather say normal language. Tau naught, we will call it as, tau is a shear stress, that is a universally accepted nomenclature. Tau naught is shear stress at wall, or we can say wall shear stress. Tau is equal to turbulent shear stress. At wall you will have tau naught. If you see the previous figure, at wall you will have a tau naught here. And as you move further away from wall to center, the velocity increases, and turbulent, the flow changes from laminar to turbulent, depends upon the Reynolds number. Then that there also shear stress will be there. That shear stress we can call it as a turbulent shear stress. At wall the shear stress is called as wall shear stress. Then dP by dx. Please listen to this nomenclature. We will be using regularly in this lecture. It's only an introductory lecture for turbulent flow. I will be taking at least not less than 7 to 10 lectures on this topic. dP by dx is equal to pressure gradient. I told you, when you change something with respect to change in something, that is called as a gradient. If it is time, it is called as rate, and if it is distance or space coordinate, then it is called as space measurement, then it is called as a gradient. This is pressure gradient. Then du by dy, velocity gradient. Now, velocity gradient I have already shown you. How to talk about the pressure gradient? I'll say it is x1 and it is here, it is x2. Fluid is flowing like this. The pressure at x1 is P1, pressure at x2 is P2. The distance between x1 and x2, let me say x, delta x. Then what will be delta P? Delta P is equal to change in pressure between two sections is P2 minus P1. Absolute value I have put because P1 is greater than P2, P2 is greater than, let us be interested in the numerical value, and directions we will see afterwards also. And delta x is equal to x2 minus x1. Let us put absolute value for this also. Then dp by dx will give you a pressure gradient. If you don't put the absolute values, then it will be the direction of the flow also. Always fluid flows from higher pressure to a lower pressure. From a higher pressure to a lower pressure. Then dp by dx is pressure gradient. In the small diagram itself, I am trying to explain the total turbulent flow so that you will understand the concepts clearly. Then du by dy is velocity gradient. Then there is one particular constant called as kappa. This is kappa. It's not K, it's kappa. Kappa Prandtl constant. Its value you can take as 0.40. It's a standard value from literature. You can take it as 0.40. Very important. Please remember this. Please remember this. This constant is not given also. Take it as 0.4 and go on your calculations. Otherwise you will be stuck somewhere. Please remember this. Next comes, for example, y is the distance from the wall. Don't get confused. Wall means a vertical wall in your house or in your rooms. It's a wall is the edge of the pipeline also, as I told you, inner edge of the pipeline. The distance from the wall. Let us see previous diagram. This is y. This distance is y. The distance from the wall, please remember, distance from center of the pipeline is different, distance from wall is different, distance from wall is y. Please make it very, very clear. Y is distance from wall. Let y is equal to distance from wall. Then there is one item called as L, Prandtl mixing length. L, it is also very, very, very important. Prandtl mixing length. We are not going into kappa into y. Very important formula. This is equal to kappa is 0.4. We have already known. Very, very important formula. If you know what is a Prandtl mixing length, this turbulent laminar, I have already shown you the laminar sublayer. That means whenever fluid flows in a pipeline, it starts flowing in a pipeline. The profile, velocity profile will not be completely formed at single instance. It takes a little bit of length before a velocity, mathematically analytical velocity profile, I can rather say. If you see, when you see the flow in the pipelines or flow somewhere, fluid flow, due to turbulence or high velocities or whatever may be the reasons, the flow is not that easily mathematically, analytically modeled. These are all models, what we are doing in fluid mechanics. These models may not be practical. Hence only empirical formulas are, very numerous number of empirical formulas are there in fluid mechanics. This Prandtl mixing length also up to the length of 0.4 y. Y is already known to you. Y is the distance from the wall. The velocity is known and the velocity gradient is also known. These are all tangents to the parabolic, that curve. But these are also analytical modeling. In the analytical modeling, when we have gone, then Prandtl told up to the length of 0.4 y, up to the length of 0.4 y, the laminar turbulent modeling and the velocity profile perfect modeling is not possible. Hence, we cannot directly find out the velocity profile, and there will be some amount of difference between the practical values and the modeled values or theoretical values. Next comes y is the distance from the wall, L is Prandtl mixing length. This Prandtl mixing length, why it is required, I will tell you. To find the shear stress, I told you tau is equal to turbulent shear stress, and we want shear stress at a distance of y. Wall shear stress is there. We want shear stress at a distance of y. How to find out the shear stress? What is the formula for a shear stress from your basic fluid mechanics? You please tell me. When you know the du by dy, when you know the velocity gradient du by dy, from Newton's law, we can say that tau is equal to, this is also, tau is equal to, it's also very important formula. Tau is equal to rho L square into du by dy whole square. This is also very important formula in turbulent flow calculations. L is equal to Prandtl mixing length. You come to know from y, the distance from the wall. At that particular distance from the wall, you can calculate the Prandtl mixing length. And once Prandtl mixing length is known, then shear stress at that particular point y can be calculated by using this formula. Tau is equal to rho L square du by dy whole square. Don't get confused with the wall stress. Wall shear stress is different from the shear stress at point y. Shear stress at point y is tau. This is tau. Near wall it is tau naught. Differentiate between tau and tau naught. Now you got shear stress at point y. What are the points we have to know to really understand the fluid flow exactly? Then, centerline velocity I have spoken about. What is the centerline velocity? Centerline velocity is u max, that is maximum. This is centerline velocity, u max. Then mean velocity. Mean velocity, usually we are given the flow rate in a pipeline. That flow rate is in cubic meter per second by cross-sectional area. This is equal to mean velocity of the pipeline. Then there is something called shear velocity. There is something called shear velocity. U star, that is shear velocity. Due to shear, there will be velocity. Due to shear, there is a reduction in the velocity of the flow. That is Ux is shear velocity. Here, wall shear we have told, this shear at y we have told, and we have not spoken about the velocity reduction or velocity increase. Because of the lesser shear and higher shear, there will be velocity reduction. That Ux is the shear velocity. The velocity, because ultimately we are talking about the velocity profiles. These two control the Ux. U star. U max is the centerline velocity. U star is the velocity because of the impact of the shear stress. And V mean is the velocity because of the flow. From flow and cross section we calculate the V mean. And ordinary U without any suffixes and anything, U is velocity of the fluid flow. Now we got how many velocities? U is the velocity of fluid flow. U star is the shear velocity. U max is equal to center line velocity. Capital V is equal to mean velocity. And the relation between all these four velocities, the changes are due to shear, friction, the changes are due to various factors. The changes, why these changes, and how much is really contributing to the real flow of the fluid, how much I will be getting the flow at the destination, these are all depends upon this. Now, once we have a clear idea of how to calculate these and how the roughness factor, how the velocity gradient, how the smoothness of the pipeline, how the turbulence of the pipeline affects, then once we know about all these four velocities, then we can say we know the real velocity profile of the flow of the fluid, and we can say this is the origin and this is the destination. At origin I can have any velocity V, but as destination I have something called V over Vd is how much. This is depending upon all this effect of this shear velocity, centerline velocity, mean velocity, which velocity to be used where, which velocity is to be how much, and which velocity is to be used where, and how it is to be used. This is what about turbulent flow in pipelines. Next comes, let us say, roughness. I have just spoken about roughness, epsilon or K naught. This is the roughness. Now, a pipe is there. In this pipe, roughness is there. This is epsilon, this roughness. When you use the cast iron pipes, what happens? Due to usage for longer periods, it develops because of the dissolved solids and because of the what you call sticking of extraneous material to the surface, in the inner surface. This roughness increases, and from the roughness we can say that flow is getting reduced. That means V is affected, velocity is affected, ultimately velocity. If velocity is affected, automatically Reynolds number changes. And you see from continuity equation, Q is equal to AV. If roughness increases, A gets reduced. Roughness increases implies diameter decreases. Diameter decreases means A decreases. A decreases means from continuity equation, velocity increases. When velocity increases, Reynolds number increases, turbulence increases. Turbulence increases means uncertainty in flow increases. Uncertainty in flow increases means life of the pipeline reduces. It implies When the life of the pipeline is reduced, uncertainty increases. What happens? Commitment as an engineer by you, commitment for delivery gets affected. This is the total meaning of learning this fluid mechanics, turbulent flow. Why I have taken turbulent flow as the first topic, you might have understood by this time. With this, I want to close for today because it is the first day. From my side, there are many other definitions which I will give in the second lecture. And please look forward for my second lecture. In that, I will be talking about the laminar sublayer, then friction factor, Colebrook equation, and then u infinity, and then velocity at y is equal to 0, distance from wall where velocity is equal to 0, y dash. Then I will be talking about the rough turbulent flow, and I will be talking about this laminar flow and turbulent flow. These I will be taking up in the next class. With the reminder that the question whatever is showing on the screen is to be solved. Today I am not solving it. I have given sufficient clues to you how to solve and what formula to be applied. You try to solve it by using your knowledge in fluid mechanics, and by chance, if you are unable to solve it also, no problem. In the next class, maybe in a couple of days, I will be releasing the lecture. In the next lecture, I will be solving this question, which is a very good conceptual question. And please review my engineering mathematics lectures also.